In this tutorial, we're going to learn how to estimate a paired samples t-test in R, where a paired samples t-test is sometimes called a matched pairs t-test, a dependent samples t-test, or a within subjects t-test. So the paired samples t-test is part of a larger family of analyses that are aimed at comparing means, and it is used to compare whether the mean of the differences between scores on two continuous variables or outcomes with the same set of cases, if that mean of the difference deviates from zero. So often in this context, the two outcome variables are actually scores from the same assessment measured at two different time points. A paired samples t-test would, however, also be appropriate when the two outcome variables in question are both in reference to the same set of target cases, where a case could be an employee, an individual, or whatever, however you define a case as a unit of analysis in your particular context. So when we do find that two outcome variables in question are both in reference to the same set of target cases, this would then suggest that these two variables are dependent as opposed to independent, because they're essentially referencing the same thing and it has the same cases are referencing those two things. So for example, if employees self-rated their own performance and then their supervisor rated those same employees' performance levels using the same type of performance evaluation tool, then a paired samples t-test would likely be appropriate, assuming your goal is to determine whether there are systematic differences in terms of how employees rate themselves compared to how a supervisor rates them. Well, in this tutorial, we're going to be focusing on the training context and specifically the training evaluation context. And in the context of training evaluation, the paired samples t-test is typically appropriate for evaluating what's referred to as a pre-test, post-test without control group design, such that the pre and post-test measures represent the administration of the same training outcome variable or measure before and after training, where all trainees, all those people who participated in the training program, in other words, complete both measures or both outcome measures before and after they complete the training program. So as background, there are different types of t-tests, and in this tutorial, we are again focusing on what's commonly called the paired samples t-test specifically. I have another tutorial in which I demonstrate how to go through the independent samples t-test, which is used when you have two different independent groups and you want to know whether the difference between those two means is statistically significant or not. So the data we're going to be working with here today, and I've structured the data as follows here, which is that there are two different columns or variables for the pre-test and post-test. These are our two dependent outcome measures here. In other words, these are paired here. And alternatively, sometimes you'll see the data presented in long format. This is currently in wide format, and that would look a little bit different, but you can still analyze the data and they would still be appropriate for a paired samples t-test. But this is probably the easiest wide format to work with when you are doing a paired samples t-test, at least based on my personal experience here. So what you see here is the first variable is an employee ID unique identifier variable. We're not really going to use this today, but this is mainly to signal to us that these are unique employees or trainees that we're working with here today, where each employee or trainee has their own row of data. Now, the next two variables are the substantive variables we're going to be focusing on, which are pre-test and post-test, both with the capital P and both with the capital T for test. And what you'll see here is that each individual employee or trainee has scores on both of these. In other words, they have paired data. So these are not independent groups for these two variables here. These are the same employees here that are participating in both the pre-test and the post-test. So remember, this is a pre-test, post-test without control group. So there's no control group here. We're just giving everybody the same training and we assess them before and after the training program on the same type of test. And let's assume that whatever this test is measuring, whether it's administered before or after, is the same type of learning outcome or behavioral outcome or reactions outcome that we wish to evaluate the training on. Okay? So our question then is going to be with the paired samples t-test, and this is how we can test it, is the mean of the differences. So if we were to create difference scores for each person, so for example, the first person would be 66 minus 43. What's the difference there? Well, that's 23. If we take the mean of those differences, then will that mean of the differences be significantly different from zero? If it is, then that provides us with evidence that perhaps there is a significant change or increase or decrease in terms of pre-test to post-test scores from before to after training, respectively. Okay, so the name of this data file that we're working with here today is training evaluation underscore pre-post only, with all capital letters beginning each word there. And so make sure that you save this into a folder that we can subsequently set as our working directory when we get into RStudio. So I have already saved it to my folder that I'll end up setting as my working directory, which is my H drive, our workshop folder, and you can see it saved here. All right, so now let's move over to RStudio. So I just opened it here. We have access to it. We can see our console here. We have some version information about the R version on which this RStudio is sitting on top of. Let's go ahead and clear out that console by going to Edit, Clear Console in the dropdowns. Again, that's Edit, Clear Console in the dropdown menu. All right, we don't need to do that, but I like to do that just to start off so we have this blank slate that we can start with here. The next thing we're going to do is go to our dropdowns and do File, New File, and R Script. Again, that's File, New File, and R Script. This allows us to open up an R Script editor window where we can write our code, our annotations, and which can tell a story to us, to other people we're collaborating with, and generally allow us to make annotations that explain why we're doing something, how we did something, or why we interpreted something in the way that we did. I'm going to start off with a hashtag annotation in which I use the pound sign to indicate that I'm doing anything that comes to the right on that line of code is an annotation and won't be treated as a command by R. I'm going to type in really and remind us what we're doing here today, which is we're going to be focusing on a paired samples t-test in R. And specifically, we're going to be focusing on a pre-test, post-test without control group design from a training evaluation design context. And that type of design can also be applied in other contexts when we're evaluating things outside of a training context. Okay, so the first thing we're going to do is set our working directory. And to make things simple here, I'm just going to use the drop-down menus by going to Session, Set Working Directory, Choose Directory. Again, I'll do that really quick. I moved through that quickly there. It's Session, Set Working Directory, Choose Directory from the drop-down menus. And I'm going to go to the drive and the folder where I saved that data file that I showed you earlier, and it's in my H drive, our workshop folder. You can't see it when you open up through these drop-down menus here, but if you save the file in this folder, it should be in there even though you can't see it, so just click Open. And so down here in your console, you get confirmation that you have set your working directory. You see it here actually printed below the console title there, and then you see it in your console command next to the command line right there. And I'm just going to copy that and paste it below here. What this does is just means the next time that after I save this R script, I close down RStudio, I open up a new session, I don't have to use these drop-down menus again when it comes to setting the working directory so I can read in the data that we're about to read in. Okay, so the next thing we're going to do is read in the data file. And so what are we going to call this data file here today? Well, we can call it whatever we want, but I'm just going to keep it simple and call it TD for training data, and that's TD, lowercase t, lowercase d. We use a left-handed arrow operator to assign the data frame that we're about to read in to this object that I've called TD here. You can call it whatever you'd like. And we'll use the read.csv function from base R, and because it's from base R, we do not need to install an additional package to access this function. All right, so within the parentheses for the read.csv function from base R, we just need to type in single argument here. And first we start with quotation marks within the parentheses, and within those quotation marks, assuming that we have set our working directory and that our working directory that we've set contains the data file we wish to read in, we just need to input and type in the exact name of that data file. And make sure it is a comma separated values file or .csv if you're using the read.csv function. I'm actually going to go to my working directory folder right here, copy the exact name of that file, paste it in here because it's kind of a long one. I want to make sure that I get all the spacing and everything correct there. And then add .csv to the end of it and within the quotation marks. So do make sure that you put period .csv there for comma separated values file to remind the read.csv function that you're working with a .csv file here. Okay, so now we're ready to run that line of code to read in the data and assign it to the object called TD. Now if we look over in our global environment here, we see we have a new object. It has 25 observations, or in other words, cases. In this case, cases represent individual employees or trainees, however you'd like to think about them. And we have 3 variables. Let's take a peek here, make sure it read in. This should look familiar. We've got our employee ID, unique identifier variable here. And then we have our 2 focal variables here, which are a pre-test variable and our post-test variable, both with a capital P and a capital T here. And let's assume that the scores on these 2 tests could be a maximum of 100, which means you learn more of whatever these tests are measuring. all the way down to 0, which means that you essentially learned nothing, at least according to these measures. Okay? All right, so the next thing that we're going to do is we are ready now to estimate our paired samples t-test. Okay? And to do that, we first need to actually make sure that we have installed and accessed our lessR package, because we're going to be using a function from the lessR package called ttest, very appropriately named. And so if you haven't already, make sure that you use the install.packages function from base R, and then within the parentheses and then within quotation marks within those parentheses, type in the exact name of the package that we wish to read in, which is lessR with a capital R. And I'm not going to run this because it can take a little bit of time and because I have recently installed and updated lessR on my computer. But if you have not used lessR yet, definitely run this and install it. What you will need to do is use the library function if you're opening a new session here. And within the quotation, or within the parentheses rather, of the library function, type in the exact name of the package you wish to read in, which is in this case the lessR package that we've installed. And that's lessR with a capital R here. You don't need quotation marks around the package name here. We can click run here, so definitely run this line of code right here. And the lessR package is a little bit unique. When you load it, you will get, when you open it in a new session, and this is the first time you've accessed it within a new session, you're going to get some red font down here. Typically, that's not a good sign, but here, this is just information about the package, who to contact, which is Professor David Gerbing at Portland State University School of Business, who created and develops this package, as well as the website as well to learn about new features of this package. Right here, it's indicating to me that I am using an older version of R underneath RStudio here. I'm using 4.0.2, whereas the lessR package was built under version 4.0.3. It's not going to make a difference here today, but this is a good reminder for me that I need to update my base R package that sits underneath my RStudio interface here. Okay, so now that we've accessed the lessR package, we're ready to access functions within them and deploy them. So we're going to use the ttest function, and this is the same ttest function you would use with an independent samples t-test. We're just going to write the script, or the arguments are going to be a little bit different structure here than what if you followed along with my independent samples t-test tutorial, it's going to look a little bit different here. And there's some important distinctions that we need to be aware of as well. Okay, so within the ttest function, that's ttest all lowercase there. The first argument is going to be our first outcome variable. And so in our case, this is going to be our pretest. And I recommend if you do have a repeated measures design like this, where there's a pretest and then a post-test, put your first variable that comes first temporarily or in time first. That's your first argument. So in our case, it's pretest, and post-test is going to be our second argument. And part of this is because the mean of the differences will be calculated in lessR by taking the second argument minus the first argument. Okay, so first argument is pretest with a capital P and a capital T for test. Second argument, and make sure you get the exact spelling of your variables correctly, is post-test with a capital P for post and a capital T for test. Add another comma to separate the second argument from the third argument. Third argument is data equals, and then the exact name of the data frame from which both of these two variables you entered as your first two arguments come from. So it's TD for us. We read in the data frame with our paired samples data here from a pre-test, post-test without control group design, and we called it TD, lowercase, TD there. And then add a comma. Our last argument will need to specify this, which is paired equals true. So this is an important distinction when we're using the ttest function. As a paired samples t-test, we need to make sure that we include this argument and state paired equals true, which indicates that our outcome or our variables here are paired, meaning we have the same cases or observations, or in this case, employees or trainees, have scores on both of these. Now we're ready to run. So put your cursor anywhere on the line, or you can highlight the whole line and click run. Okay, and let's take a look and see what we find here. Well, first, let's take a look at visually what we see. You get this lollipop plot here, which just shows you, maybe it'll be easier to see here. This is just going to show you the difference. So the blue dot here is your pre-test, your orange dot is your post-test, and it just shows you the magnitude of the difference between those. And in some cases, you might even see these flipped, like down here, someone's post-test score was actually lower than their pre-test. Okay, and so each one of these lollipops here represents a unique employee or trainee in this context. Now, if you zoom over here, and you can export any of these if you'd like as well, these plots that come default. We're not going to focus a lot on these, but here's the distribution. And basically what we're testing here with the paired samples t-test, which is also sometimes called a one group or a single sample or one sample t-test, is whether or not the mean of the differences here, the mean of those different scores, is different from 0. Okay, so does this distribution, the mean of the distributions differ significantly from 0? That's the customary cutoff point, is setting that, comparing it to 0. Okay. All right, so now we are going to get into the output of the function, which you see here printed in your console. And we'll work through each section, which is laid out really nicely in the lessR package here. A lot of these functions have great output, really descriptive, and provides a lot of information by default that with other types of functions from R, you could also do the same things, but you'd have to run multiple functions and additional arguments and so forth in order to get the same thing. So first you'll see the description section, which is our descriptive statistics section, and you'll see just one line here, which is the difference. And so what this represents here is the difference between your post-test scores minus your pre-test scores. So whatever variable you put second here, it's scores on this minus your first argument variable. And here you see number of missing, so no one is missing a different score. And so that means that everybody, all 25 people, N of 25 here, these employees that participated in the training, they have both a pre-test and a post-test here. So what is the mean of the difference here? It's 19.64, okay? And the standard deviation is 11.597. So all we did essentially behind the scenes with this function is you can think of it like this. Created another column here, let's say called difference score, that was just for each person or each row here, took their post-test minus their pre-test. So in this case, 66 minus 43, that person would get a different score of 23 here. And then you'd move on to the next person and you'd have a whole column here. If you take the average of those differences, that's what we're talking about right here. This is what this mean represents here. So we're seeing that because this is positive, because we put the pre-test as the first argument, post-test as the second argument, and this is computed by taking post-test minus pre-test to get this difference. This means that scores on average, at least descriptively speaking, seem to have increased by 19.64 points. And the standard deviation of that distribution of scores is about 11.60 or 11.97 to be a little bit more precise. Okay, so descriptively, this is the mean of the differences here. But can we treat this as being statistically significantly different from 0? Well, that's where we'll get down to eventually to our inference section, and we'll be able to determine whether we have evidence that in the underlying population, whether it's appropriate to infer that this mean of the differences is significantly different from 0, or in other words, did people significantly increase their scores on the test from pre to post training? All right, so now we have the normality assumption down here, and we can see that we just have one statistical assumption test that we're going to be focusing on here, which is the Shapiro-Wilk normality test. Here we see our test statistic here, which is the W, and it's 0.9687. That's not really meaningful on its own. What we're interested in is the p-value, which is associated with that W statistic, which is 0.6134. And I'm going to go ahead and type in, or rather paste in, some more precise information here so you can see this written down, because the language gets a little technical here and I want to make sure you can both hear and see it. Okay, so the Shapiro-Wilk normality test is used to test the null hypothesis that a distribution is normal. In other words, do you see that bell-shaped curve? So accordingly, if the p-value associated with the test statistic W is less than the conventional alpha level of 0.05, then we reject the null hypothesis and assume that that distribution is not normal. If, however, that p-value associated with the test statistic called W is greater than 0.05 or equal to 0.05, then we fail to reject the null hypothesis, which means that we do not have statistical evidence that the distribution is anything other than a normal distribution. In other words, if the p-value is equal to or greater than our alpha level of 0.05, and that's two-tailed, then we can assume the variable is normally distributed and can feel satisfied that we have met the statistical assumption of normality for that particular distribution. Okay, so In this case, we found that the p-value is equal to or greater than 0.05, which is that conventional alpha cutoff level for a two-tailed test. And so therefore, we would fail to reject the null hypothesis that this is a normal distribution of the mean of the differences here. And so in that case, we are left with accepting that this appears to be, or at least we don't have evidence to the contrary, statistically speaking, that this is a normal distribution in terms of this right here that we see visually, the distribution of the mean of the differences between the post-test and the pre-test scores. All right, so right here, we seem to have met the statistical assumption here. And so we can proceed forward. We should feel more confident in proceeding forward and actually interpreting our paired samples t-test. So we haven't even gotten to the paired samples t-test, but it comes down here in our inference section. So here is the inference section. You can think about this meaning the inferential statistical analysis section, meaning this is where we're trying to make inferences about our underlying population of employees in this case, and whether the differences, and specifically the mean of the differences between those pre-test and post-test scores relative to when people took training, whether that mean of the differences significantly differs from 0. Okay, we'll kind of skip through this first information here. Here's the t cutoff for the 95% range of variation, and here's your standard error of the mean, which you can see here represented as SE equals. We're not going to focus on that here. Instead, we're going to focus on these two lines here first, okay? And so the first is the hypothesized value for H sub H naught or H sub 0 here, which is your null hypothesis, is mu, or the population mean, is equal to 0. So that's by default. Typically, this is what our default is. You could change this if you wanted, but typically we're trying to test something against whether the mean of the differences is significantly greater or less than 0. All right, so the next line down here, knowing that this is our null hypothesis, is a hypothesis test of the mean here. So we get our t-value, which is 8.468, the associated degrees of freedom here, which is just our sample size, which is 25 here, minus 1 when you have a paired samples t-test, which equals 24 here. And then we have our p-value, which is 0.000. It's not actually exactly equal to 0 here. It's just that the p-value is very, very small, and it is still greater than 0, but it's because of rounding here with the decimal places, we just don't see the last digit. So conventionally, if you were writing this out, you'd say the p-value is less than 0.05 or less than 0.01, 0.05 being that conventional alpha level that I've referenced already. So what does this mean right here? Well, if our null hypothesis is that the mean of the differences is 0, and because our p-value associated with our t-value here is less than that conventional alpha level of 0.05, this would mean that we reject the null hypothesis that the mean of the differences is equal to 0, which then leads us to conclude that the mean of the differences is statistically significantly different from 0 in this case, because this p-value is less than 0.05. If, however, this p-value had been equal to or greater than 0.05, then we would conclude that the mean of the differences was, from a statistical perspective, the same as 0. Okay? So what does this mean? Well, we need to interpret this in light of the mean of the differences here. And again, it matters which variable we put in which argument position. Because we put post-test second and pre-test first in terms of the arguments, it is again post-test scores minus pre-test scores. And so this positive mean of the differences value here means that there was an increase from pre-test scores to post-test scores. So from before training to after training, the test scores actually increase. And what we see with this paired samples t-test down here and its associated p-value is that that is a statistically significant difference, mean of the differences. So that increase from pre-test to post-test, that is something that we can treat as being statistically significant. Okay, so that is a meaningful difference right there. Now below this, you can also find your 95% confidence interval for that mean of the differences as well. So we know that the precise point estimate is 19.64. Well, in the middle of that, it's the lower and the upper limits of the 95% confidence interval would be 14.853 to 24.427, respectively. Okay, so because our p-value here is less than 0.05 for our statistical significance test, our inferential statistical significance test here for our paired samples t-test, it is then appropriate to move on and interpret the effect size or practical significance. So what we learn from this is that there is a difference in terms of that mean of the differences is significantly different from 0. Our next question is, well, how big of a difference are we talking about here in an absolute sense? If you were to have not found statistically significant finding here, in other words, if the p-value were equal to 0.05 or greater than 0.05, we typically would not move forward and then interpret the effect size or practical significance. Okay, so moving down to the effect size or practical significance here, we already know this value. This is the mean of the differences, post-test minus pre-test scores. If we took that vector and took the mean of it, it's 19.64 here. Well, what does that mean in terms of a standardized different distance here, standardized mean difference, or Cohen's d? Well, Cohen's d here is 1.694. So what does that mean? Well, Cohen's d is an effect size, which means that we can compare different Cohen's d's values together, and that will give us an idea of, in an absolute or practical sense, how large of an effect we're talking about here. So it can be hard to remember, but so I'm going to type this out here for you, but common Cohen's d cutoffs or thresholds and their qualitative descriptors are as follows. If the absolute value of Cohen's d is about 0.20 or greater, that would be considered small. If it's 0.50 or greater, that would be considered medium. If it's 0.80 or greater, that's considered a large effect. So down here we see Cohen's d for our mean of the differences of 19.64. Cohen's d is 1.694. So that standardized distance there is going to be definitely greater than our 0.80 threshold or cutoff for Cohen's d. And so it's at the very least a large effect, or this statistically significant effect also has large practical significance. And you might even go so far as to say this has a very large practical significance here. Okay? And so that wraps up how to actually interpret the output from the t-test function from lessR when you are doing a paired samples t-test with that function. The next thing I'm going to show you how to do is a data visualization bar chart. So when you do find a statistically significant effect with a paired samples t-test, you may decide to plot that. I do caution you against creating any kind of data visualization when you don't find a statistically significant finding. All right, so in order to do this, this is going to be a little bit trickier than when you followed along. If you did follow along with my independent samples t-test video or written tutorial, you'll find that in order to we have to get the data into a proper format in order to use the bar chart function from lessR in order to present the mean of the differences visually here, okay? And so the way that we're going to do this is as follows. The first thing we need to do to prep our data is we need to create a vector of means for the first and second outcome variables, okay? And I'll show you what this means here. So the first thing we're going to do is we're going to use the C function here. And the C function you can think of as being combined. This is how we create a vector, so that we're going to create a vector of means. And this is pretty simple here what we're doing. We're taking the mean function from base R, and that's MEAN, so we're taking the average, and within the parentheses in the mean function, just type in the name of the data frame, object, $ operator, and the name of our first variable, which was pretest, with a capital P and a capital T. Make sure you get the spelling correct there and the case sensitivity correct there. So this is what we have here. And if you had any missing data, you could add in na.rm equals true, and it would handle that accordingly. In this case, we don't, so I'll just keep this simple visually here. And what we're doing first, and you can actually just run this to see what will happen. I'll just run the mean function. See, we get the mean, and this is the mean of our pretest scores, okay? So then add a comma between these two parentheses here, so the comma after the parentheses for the mean function. And then we're going to do the same thing for the mean function, and we're going to use the mean function again, but this time we're going to do name of the data frame, $ operator, and post-test, which is the exact name of our second variable here, our second outcome variable. And if we run just this, you'll see that here is the mean of the scores for the outcome variable here, or the post-test outcome variable. Okay, so one thing to note here is that the $ operator tells R that this variable, for example, the pretest variable, belongs to this data frame object here. So that's why we're using that $ operator in both cases here. I'm going to go ahead, now that you can see the basic logic here, I'm going to add in that second argument to each one of the mean functions here, which is na.rm equals true. And this is just in the event that you had any missing data. So I'm just adding these in here. And so hopefully this is clear now. So if we highlight all of this and click run, you'll see it returns a vector of our mean scores for the pretest and our mean scores for the post-test there. So 52.72 and 72.36. The next thing we want to do here, though, is use the left-handed arrow operator to assign that vector to an object that we can subsequently reference. I'm going to call this object pre, post, and means here. Okay, so it's pretty descriptive here. So pre, post, means, and I'm going to click run. And now I have an object here. If I just run this object and print it to our console, you'll see those means return. So that should look pretty familiar here. Okay, so the next thing that we're going to do is we are going to create a vector of names in this case corresponding to the first and second means above. In other words, we're going to create labels for these two means. Remember, first we created the pretest mean and second the post-test mean. The order matters here. So to do that, we're going to use the C function again. And within the C function, you don't have to just use numeric data. You can also use text or character data as well. As the first, within quotation marks, I'm going to create a meaningful name for the first mean. So the name of the variable is pretest, but I'm going to do that except add a hyphen to make it a little bit more conventional in terms of how we'd write it. So put that in quotation marks because it's text or character data. Then add a comma outside the quotation marks and separate that from the second argument of the C function here, which is the name that you wish to give to the second mean, which happens to correspond to our post-test variable up above here. So within quotation marks there, I'll just do post-test. And so if we run this as it is, this line here, you'll see that it returns the vector pretest, post-test. So these are our labels for the means, the names for them in other words. And then I'm going to use the left-handed arrow operator to the left of the C function there, and I'm going to then assign this vector of mean names here to an object I can subsequently reference. I'll do mean names, just MEAN, NAMES, no hyphen or underscore there. Okay, and run that there. And so if now, since I've assigned that to the mean names function or mean names object I named here, and I click run, just highlighting the name there, you'll see in my console it returns the vector of those two labels or titles that I wish to eventually apply to those means. Okay, so what is the next step here? The next step is going to be to create a data frame from the two vectors that we created above. So we created this first vector here with the pre and post test means, and the second one has the names we'd like to add to them. So how do we create a data frame? Well, it's actually pretty simple in R. We can use the data.frame function from BarChart, and that's data.frame all lowercase. And simply in our case, we'll just, at the first argument is going to be copy in. Actually, let's start with the mean names here. Let's copy in the mean names. So that'll be the first argument there. So that'll be the first, so that's the first argument, which will correspond to the first column in the data frame we're creating. And then I'll copy the other object here, which is for the mean values themselves, the numeric values. So just separate these two arguments with a comma like we do in R. Okay, and so if you were to just run this as it is, you'll see it returns down here the data frame by itself. And so you'll see we have two columns or two variables, the mean names, pretest, posttest, and their corresponding means. It's a very small data frame. But let's assign this data frame object, or this data frame rather, that we've created here to an object we can subsequently reference. And this is going to be, let's call it means df. Okay, so means data frame is how I'm thinking of that. So I've just called it means df here. I've used the left-handed arrow operator to assign this data frame to this object that I'll subsequently reference in the BarChart function. Click run. All right, the next thing that I'm going to do is let's clean up our global environment here a bit. I want to make sure, it can be a little bit confusing sometimes when we have things that are similarly named in terms of objects in our global environment. I want to remove the two objects we created. We don't need them anymore because now we have this data frame that's combined these two vector objects of mean names and pre-post means that we created there. Let's remove those from the global environment because we have here, this is what we really need as input for the BarChart function we're going to use is this data frame object that we call means df that we just created. Okay, so I'm going to remove the two vector objects from the R global environment. Okay, and we'll just keep this simple and use the remove function from BarChart, it's just REMOVE all lowercase, and just paste in the exact name of these two vector objects. So the first one is pre-post underscore means here. Click run, watch what happens over here. Now that is gone. And the next line is going to be remove. And then mean names is the other vector object I just want to clean up from our space here. Click run, and now that's gone. So now we have a tidier space here in our global environment. Okay, so now we're finally ready. So this is a lot of data prep just to get to a simple bar chart, but sometimes you have to do it this way. We're ready to create our bar chart. We're going to use the BarChart function from lessR. If you've already accessed the lessR package above, you don't need to access it again within the same session to access the BarChart function. It's BarChart with a capital B and a capital C here. Okay, so the first thing that you need to enter as an argument is going to be what is going to be your x-axis. Okay, so that's going to be the mean names. So your pre-test, post-test. So do x equals mean names. Okay, and where is this coming from? Well, if you look at your data frame object, it's this right here. Our variable name is mean names here. So we want to reference that column, and this is going to be set as our x, or rather our x-axis. Comma, separate it from the second argument, which is y equals, which is going to be pre-post underscore means here is our second variable. So make sure you get the spelling exactly right there. So it's pre-post underscore means. And our third argument is data equals, and the exact name of this data frame is means df, from which these two variables come from that we just referenced as the first two arguments. So means df, okay? And so watch what happens if we just run this by itself. So this is kind of the default, not super cleaned up bar chart, but basically instead of representing a single column that's the mean of the differences, sometimes it's nice with the pre-test, post-test, without control group design here to just represent the mean of the pre-test scores, the mean of the post-test scores as separate columns, assuming you found that the mean of the differences between these two is significantly different. And so here, this nicely shows that the post-test score, there seems to be an increase from pre-test to post-test. So from before training to after training, test scores seem to increase here, which corroborates, or at least it dovetails, rather, with what we found from a statistical perspective. Okay, so we can continue to build on this by, let's add more meaningful x-axis labels and more meaningful y-axis labels. So we can use the xlab equals argument for the function. So xlab, which stands for x-axis labels, equals, and then within quotation marks, just type in something that's more meaningful for the x-axis. I think time, I'll just type in time of test, okay? So pre-test, post-test, that's what I'll call there. Then comma, and then ylab equals, and this is your y-axis label here, and ylab equals, and then quotation marks, and what do we think would be a meaningful label here? Well, these are test scores here, and specifically these are the average or the mean test scores. Let's just call this within the quotation marks average score. You can call it whatever you would like within the quotation marks there. Okay, put your cursor anywhere within the function parentheses or on one of the lines here, or you can highlight the whole thing and click run. And now we see we've just updated these with more meaningful labels here. You can zoom and get a better look at it there. And so now this is a nice visual depiction of what we found. Okay, so the next thing that we're going to do is we are going to, if you'd like, you can export this and save it as an image or a .png file specifically, or as a PDF, or you can copy it to a clipboard if you want to paste it into a document or into a presentation or something like that, and just copy the plot like that. And you can change the dimensions as well, the width, the height, and the aspect ratio. All right, so this has been a tutorial on how to estimate a paired samples t-test in R, and specifically we focus on the context of training evaluation, and when we have a training evaluation that is a pre-test, post-test without control group design. And so we learned how to apply the t-test function from lessR, and then because we found a statistically significant the mean of the differences was statistically significant between our pre-test and post-test scores, we then decided to visually represent that difference that we found that was statistical using a bar chart, which you see pictured here. So this wraps up the tutorial.